Hello, my name is John Bozard, and this is my Physics 2212 Lab 4 on Faraday's Law. The purpose of this lab is to gain a better understanding of Faraday's Law and magnetic flux by analyzing a bar magnet as it falls through a tube of aluminum foil. I will record the total time it takes the magnet to fall for 5 trials and compare the average time to that produced by a computational model. The fundamental physics principles used in this lab are Faraday's Law, defined by setting induced voltage equal to -n, or number of loops, times the rate of change of magnetic flux, the Biot-Savart law, which determines the magnetic field of a loop, and Newton's second and third laws, which state F equals ma, and each action causes an equal but opposite reaction. I performed the magnet dropping procedure, as seen in the video on the right, 5 times and recorded the values in the table on the left. I found the average fall time to be 2.458 seconds. To start my GLOWSCRIPT code, I defined the necessary dimensions of the aluminum tube, such as length, radius, width, etc. Next, I implemented the magnetic field function from the previous lab with the Biot-Savart law to later be used to find the magnetic force on each ring. I then defined a magnetic flux function by referencing the equation given in an EDX video. After finding the gravitational, magnetic, and net forces acting on the bar magnet, I calculated the induced current by dividing the flux's rate of change by the resistance of the aluminum tube. Finally, I added the magnet's velocity and position over time to produce a general model. After I ran my code, 2 diagrams were produced. First, on the left, is a visual of the bar magnet traveling down the tube over time. Red represents north and blue represents south. On the right is a velocity versus time graph that displays the magnet's motion. As you can see, while the magnet is falling through the tube, it is not experiencing any acceleration and therefore has constant velocity. In the bottom left are the computational model and in-person time measurements of the magnet falling. There's a fairly large discrepancy between the two, approximately 1 second, which can likely be attributed to either miscalculation of the dipole moment magnitude in Lab 3 or an incorrect induced current value. Here's another quick look at my GLOWSCRIPT code. The link is in the description if you would like to analyze it in further detail. Once run, you can see the magnet slowly moving downward over time and the velocity versus time graph below. So, how would the motion of the magnet change if the aluminum's resistance was reduced to nearly 0? Well, Ohm's law states that current equals voltage divided by resistance. Therefore, an extremely low R value would yield a large induced current. Because current and magnetic force are proportional, the bar magnet would experience a larger force and as a result, take longer to fall through the tube. Next, if holes were cut into the aluminum, how would the current be affected? To answer this, fewer slots means less aluminum rings, which will lead to a lower current and magnetic force on the magnet. If I were to then measure the fall time, I would notice a trend of faster times. Thank you for watching.